Hey, I'm going to do some physics problems here. Number 17, chapter 5, going up to number 27, hitting the odds. That's the plan. So in number 17, we've got a little figure with a block suspended, a rope like this. And the angle is 30 degrees of this ramp. The mass of the block is 8.5 kilograms. And I want to find the tension of the cord, the normal force acting on the block, and then if the cord's cut, the magnitude of the resulting acceleration. Okay, so this is going to be right here where you learn how to make a force diagram. I think I talked about this in the force diagram solutions. This is a skill that you need. We're going to do this lots of times. Here's the block. There's my dot that represents it. And this, I'm going to make a dotted line that is in the same direction as this ramp here. That is not any kind of force or anything itself. It's just sort of a guideline there. And then I'm going to have a line perpendicular to that. So as if like this is like my x, y, or my I, j axis system. Okay? Now of course gravity is going to go straight down because gravity doesn't care what the humans are doing. And that's the force of gravity there, which I could put in the diagram if I wanted to. It's 8.5 g. In other words, 8.5 times 9.8 meters per second squared. I'm trying to think if when we talked about this, some particular forces, let's see, did we do some problems from that section? Maybe not. So maybe we need to talk for a second about that. The force of gravity, there's a lot of different ways to get at this, and oh geez, I guess this is turning into a little bit of notes here, isn't it, about this? So that's all right. So the g, which is the acceleration due to gravity at the surface of our planet, is 9.8 meters per second per second. That's an acceleration. But did you know that the units meters per second squared, a newton, of course, force equals mass times acceleration. So if you think about units, force equals mass times acceleration. So if you divided this over here, you can see that newtons over kilograms is equal to meters per second squared. And if you are, if you're Isaac Newton, or especially if you're Albert Einstein, like this is really, really, really important and very, very deep. I mean, it just seems like we did a tiny little bit of algebra there to move that kilogram to the other side. But this is actually the kernel of Einstein's general relativity here. That, well, I don't want to, that's a deep rabbit hole or wormhole or something to go down. But it's very important to understand this, that when something is falling, free falling, then it'll have an acceleration of 9.8 meters per second squared if there's no other forces besides gravity. That's our free fall acceleration. But we can also express that as 9.8 newtons of force per kilogram of mass. And that's, I think, how we want to think about it here when we're figuring out, well, how much gravitational force is there on something? What is its weight? Its weight, or gravitational force, is its mass times g. But in this case, when we're doing gravitational force, we're really thinking about it as 9.8 newtons per kilogram. So you got 8.5 kilograms, 8.5 kilograms times 9.8 newtons per kilogram. The kilograms cancel, you get newtons. That's how much gravitational force there is. So in general, gravitational force is equal to mg. And of course it has a direction downward. Okay, so I think that's good for that. You're going to do that little move, multiply the mass of something by 9.8 about a bazillion times in this class before we're done. All right, so what else do we have here? Well, the first thing I'm going to do is I'm going to go ahead and break up this And I'm going to turn this so that my little XY axis is now nice and horizontal and vertical, so I don't have to strain my artistic abilities. So I'm going to break this up straight down and straight over, but this is like the new over. So, right, notice I see a lot of students accidentally go too far down here and then go over this way, like not parallel to that. So that's why the paper tilt is helpful, I think. So how much normal force is there going to be? Well, the normal force, this block is at rest with the cord attached, and even when the cord's cut, it's going to move in this direction. There will be no motion in this direction, so these are definitely balanced. And a little simple geometry should convince you that this 30-degree angle, when we draw the diagram like that, shows up here. You can draw some triangles in there. There's like several different geometric ways you can prove very easily that this triangle is similar to this one, or that this angle is congruent to that one. I won't bore you with that. And if you make the diagram like this, the ramp angle, steepness of the ramp, will always show up at the top of the triangle, like that. All right, so this here, since that's adjacent, this is the side of this little right triangle that's adjacent to this. This is going to be 8.5 g times the cosine of 30, and this will be 8.5 g times the sine of 30. And that's some of the answers to the questions here. Let's see, what was A? What's the tension in the cord? Well, the tension in the cord must be balancing this. So setting up the diagram like this, really what we've done is we've just found a horizontal and vertical way of looking at all the vectors that makes it very easy to balance things out and see how they're balancing. So that tension force must be balancing the 8.5 g sine of 30, which is 8.5 times 9.8 times the sine 30. That's about 41.7 newtons. And B, how much normal force is that what B is? Yep. The force normale, as they say in France, is equal to 8.5 g times cosine of 30. So 8.5 times 9.8 times the cosine of 30 is about 72.1 newtons. And then part C is if there's no friction, I think there's no friction, right? I don't say anything about friction, so. Oh yeah, it says frictionless in the picture. Either that or the word frictionless happens to be sitting on that ramp above the block, but that seems unlikely. Especially, ironically, it would take friction to keep it there from sliding down. So if the cord's cut, then what's the magnitude of the acceleration? If the cord's cut, then the sum of all forces acting on this, well, that would be gone, and these two would still be balancing each other out. So the unbalanced force, or the sum of all forces, would just be this, because those are canceling out. So that would be 8.5 g sine 30. You know what? I really should have written this first. That's what I meant to do. Sum of all forces is equal to mass times acceleration, so that means sum of all forces is equal to this, which is equal to mass times acceleration. So you can actually see, you can do the math here, but the acceleration is g sine 30. So it's like the sine component of the acceleration due to gravity. It's like the sine of 30 times 9.8 meters per second squared. And you can see how that what we were thinking about as newtons per kilogram, that force sort of magically transforms itself into an acceleration there. Those two things are really equivalent. That's the kernel of general relativity, that acceleration and gravitational field strength are the same thing. That's a super oversimplification of what's going on. And of course, the real the meat of general relativity is what happens if you follow that rabbit hole. That's the opening of the rabbit hole, the equivalence principle, that acceleration and gravitational field strength is the same thing. Not only, meaning they don't just have the same units, they are indistinguishable from each other. So that is an idea, and if you if you enter that idea and follow all of the things that must be true as an implication of that, that's when things get really interesting. And that's when you win Nobel Prizes for physics and stuff. But Einstein did not win the Nobel Prize for that. Fun fact, you should look that up. He won the Nobel Prize for something much more pedestrian, in my opinion. All right, so anyway, the acceleration is just going to be 4.9 meters per second squared. Okay, so that took us a little while because of those notes there. Number 19, 500 kilogram rocket sled can be accelerated at a constant rate from rest to 1,600 kilometers per hour. This does not sound like a good idea. Please don't try this at home in 1.8 seconds. That seems really dangerous. All right, nobody asked me. 1,600 kilometers is 1.6. Oh, sorry, that's just kidding. That is 1,600,000 meters in 3,600 seconds. Just doing a conversion there. That's the same as 444 meters per second. All right, because you need SI units. And we want to know what's the magnitude of the required net force. So I guess I need to know the acceleration, right? I need to know the net force is equal to net force, and sum of all forces means the same thing. Sum of all forces is mass times acceleration, so I need the acceleration, and that looks like a kinematics problem there. So Vf is equal to At plus Vi. So the final velocity is equal to the acceleration times time plus the initial velocity. So the acceleration is 444 divided by 1.8, which is about 247 meters per second squared. And the mass is 500. So looks like we need a net force of about, oh, that's so funny. The numbers, if you don't round anything, the number I have is 12345.6.7. That's numerologically interesting. I'm going to round that to 123,000 newtons. You can, of course, use the kilo there if you want to. And the book did one less sig fig than that. They just went to 120 kilonewtons. It's a lot of force, I guess. So 21, constant horizontal force pushes a 2 kilogram FedEx package across a frictionless floor on which an XY coordinate system has been drawn. That'd be great, like a graffiti kind of scam. Go around and just spray paint XY coordinate systems all over the world. Figure 537, got a couple graphs here, gives the package's x and y velocity components versus time. And we want to know the magnitude and direction of that applied force. It's making that happen. So the acceleration in the x direction is the slope of Vx versus t, right? Which looks like it is rise over 3, I think. And the acceleration in the y direction is the slope of Vy versus t, which is, let's see, 1, 2, 3, 4, -5, I think, meters per second squared. So the magnitude of the acceleration, you can use absolute value signs to indicate that, is the Pythagorization of those, which is about 5.8 meters per second squared. And the angle would be tangent inverse rise over run. So tangent inverse of 5/3 is 59 degrees. And we're going positive x, negative y. So that is in the fourth quadrant or below blocks, below the negative x axis. And what number was that? That was 21. Oh, that's the acceleration. What are they asking for here? I'm looking at my answers, and why do they have so many answers for 21? What the heck? It's like a different problem. And they wanted the magnitude and direction of the net force. I think I just did the magnitude and direction of the acceleration, so I forgot to multiply by the mass, which is, what, 2? So got to double that. It's going to be 11.6 newtons. And of course, these two vectors always point in the same direction. So the direction is the same. And I'm looking at the book. I don't know if this is what or my little solution key here, and they've got some answers to a completely different question. So let me check the back of your book and see if that same mistake is there, so I can warn you of it. Nope. In the back of your book, they have the right thing. In my solution manual book, they have some other unrecognizable thing. So you're good. All right, 23. Tarzan, who weighs 820 newtons, swings from a cliff at the end of a 20-meter vine. Of course he does. It hangs from a high tree limb and initially makes an angle of 22 degrees with the vertical. All right. So there's Tarzan. Just going to make him a little dot. And that's 22 degrees with the horizontal. His weight, so that's the same as saying the force of gravity on him is 220 newtons. 820 newtons, rather. Sorry about that. And the length of the vine is 20 meters. Assume that an x-axis extends horizontally away from the edge of the cliff and a y-axis extends upwards. Immediately after Tarzan steps off the cliff, the tension in the vine is 760 newtons. Just then, what are the force on him from the vine in unit vector notation? And the net force on him in unit vector notation, and magnitude and angle relative to the positive direction, and magnitude and angle of his acceleration. Okay, so I think we need ourselves a force diagram here. Now we've got a tension this way, which they told us is 760 newtons. And we know that the gravitational force on him is 820 newtons. And the XY coordinate system that we're going to be interested in reporting things according to is that. So there's a couple things to say here, I think. One of them is to, of course, you've got to recognize that that's a 68-degree angle there, that when Tarzan starts to swing, the initial motion, like if you could swing him around in a circle, he's attached to here. So when something's attached to a rope, whether it's a pendulum or Tarzan or whatever, and it's allowed to swing freely, whether or not it swings all the way around, the path that it swings in is part of a circle. And that Tarzan, when Tarzan first starts to move, is going to go this way, tangent to the rope or the vine or whatever it is. It cannot be other than that. It has to be that way. Just like the boy swinging that rock around in that test question that you probably did some correcting on recently. Tarzan's path must be perpendicular to that vine. And that means if he's going from rest, that initial acceleration to get him moving must be pointing in that direction. So what that means is if he's not accelerating in this direction at all, then this and this must be equal to each other. That's 22 degrees there, right? So I think that the initial acceleration of him is the sine component of this. So I'm going to go ahead and fill that in. See, making these force diagrams is awful important. We'll have lots of practice, don't you worry. If you feel like you haven't mastered it yet, that's all right. This is the very beginning. So that's 307 newtons here. And of course, these are balanced, so that would have to be 760. And you can check that. I mean, 760 would have to be equal to 820 cosine 22. And I think they just helped us out here and gave us, there it is. There's that 760. So they just gave us a little bit more information than we needed for this. Okay, I think we can answer some of the questions now. What's the force on him from the vine in unit vector notation? Okay, so that's this component and this component. So you can do a little sine and cosine with that. It would be 68 cosine, 760 cosine 68, and then this would be 760 sine 68. So those components are I guess I have to do it. I was going to just cheat and look at the solution manual, but this appears to be, like for number 23, they have listed the answers that should have been there for 21. So I don't have the answers in front of me, so I'm going to actually have to do it. 760 times the cosine of 68 is 285 I plus 760 sine 68 is 705 J newtons. I think that's what they wanted for part A. Yep. How about the net force on him in unit vector notation? So the net force on him is this, because those things cancel out. So we need to break that 307 Newton force into its components here and here. That's the 22-degree angle. Geometry. So let's see, that's 307 times the cosine of 22, which is 285 I minus 307 times the sine of 22 minus 115 J newtons. In part C, magnitude and direction of the, is this of the net force? Yeah. So I have that already because I know it's this. So that's 307 newtons at 22 degrees below the positive x-axis. That might have been part C and D. Yeah, sorry. That's D. And then E and F, what are the magnitude and angle of Tarzan's acceleration just then? Well, so they never told us his mass, but if we have this, we could always divide it by 9.8, right? So his mass is 820 divided by 9.8, which is about 83.7 kilograms. And that's the net force on him. That's the unbalanced force right there. So that times 307 is, oops, they want to know his acceleration, so not times. So I need to do 307 since net force is equal to mass times acceleration. If I want to know his acceleration, that's net force divided by mass. 307 divided by 83.7 is about 3.67 at the angle would be same as this, 22 degrees below the positive x-axis. I better just check real quick with the back of the book to make sure I'm not telling you anything that's not true. Let's see, that was number 23. So 285,705 is good. 285 minus 115 is good. 307 at negative 22 degrees, 3.67. Rock and roll. We're all good. All right. That was 23. And 25. Sun jammin'. A sun yacht is a spacecraft with a large sail that is pushed by sunlight. Although such a push is tiny in everyday circumstances, it can be large enough to send a spacecraft outward from the sun on a cost-free but slow trip. Suppose that the spacecraft has a mass of 900 kilograms and receives a push of 20 newtons. And since we're out in space, there's no friction or any other forces. What's the magnitude of the resulting acceleration? And then how fast will we be traveling in one day, and how fast will it then, how far and how fast after a day? Okay, so acceleration is equal to net force over mass. So that's, I'm going to call that 2.2 times 10 to the negative 2 meters per second squared. And then, did you know that the number of seconds in a day is 86,400? It's easy to come up with that number, but I've seen it so many times, it's tattooed onto my memory. So that means that if you want to know how far, I guess this is the answer for part A here. For part B, is that how far does it go? Yeah. So delta x is equal to 1/2 at squared plus vit. It starts from rest, so that's going to be 0. 1/2 a t squared. So I think the point of this problem is, yeah, that's a tiny bit of force on that large object. But if that's causing a constant acceleration and you let that acceleration tick away for lots of seconds, then you're going to be doing something. So let's see. Punching some buttons on my calculator. So it looks like here I've got about 82 million meters or 82,000 kilometers. I think that's what that is that I'm looking at. I'll check in the back in a minute, make sure we're good. And then how fast is it going after that time? Well, just by the definition, you can plug that into an equation, of course, but just by the definition of acceleration, if you're doing, if your velocity is increasing from 0 at this rate per second for this many seconds, let's just multiply those together, of course. All right, that's just understanding what this equation does when that's 0. So that's my acceleration, 2.2 times 10 to the negative 2 times 86,400. 2.2 times 10 to the negative 2 times 86,400 is about 1,900 meters per second. All right. Let's see if my little document here has the right. Yep. Ooh, and I got the right answers too. Although per some kind of rounding difference, they have a 3 here. They have instead of a 2, whatever. If you're thinking to yourself, whatever, I'm going to miss that on a test. No, you're not. I don't count off for that kind of like doing everything right and then getting something that's just like a digit difference. An electron with a speed of 1.2 times 10 to the 7th meters per second moves horizontally into a region where a constant vertical force of 4.5 times 10 to the negative 16 newtons acts on it. So it's a vertical force. So I guess we could say that. It's 4.5 times 10 to the negative 16 newtons. The mass of the electron, everybody knows that, is 9.11 times 10 to the negative 31 kilograms. Determine the vertical distance the electron is deflected during the time it has moved 30 millimeters horizontally. Okay, so what is this problem about? Well, back in the day when TVs were not all flat and fancy like what you guys are used to, we had TVs that were cathode ray tubes, and basically what was going on inside one of those TVs. These are like the big box things that you maybe remember something from, like, you know, some elderly person in your life who had some TV held over from a long time ago. It is hard to find these things now because flat screen TVs have become so cheap. So the way that one of these TVs would work, in the back, like if this is the screen, this is you like sitting here watching TV, sitting on your chair with your hand sticking out. That's a weird way. Why would you watch TV like that? Maybe you have like a bowl of popcorn here. There, that's better. That's why your hand's sticking out. And you're watching your favorite show, and here's the TV. This is the screen of it. And the screen was actually made of glass, and it was a little bit convex like that. In the back of this, there was a device that basically sprayed electrons onto the screen, which is why, if you ever saw one of these things, when you turn it off, the picture on the screen would sort of shrink really quick to a little dot in the middle and then zap, disappear. And if you went and touched the screen, you would feel like this fuzz of static electricity, and you could, like, if you approached real close, you could usually get it to give you a little bit of a shock, like right after it was turned on, or turned off rather. So this thing like sprayed electrons onto the screen like really fast to change the image many times a second. And how is the beam of electrons, like how do you even direct the beam of electrons? Well, you do it something, I mean, that's kind of what this problem is about. It's a throwback to that idea. You have some kind of varying magnetic field inside here that's going to deflect the, or electric field inside here that's going to deflect the beam of electrons as it goes around there. So, you talk to some engineers and tell them what you want to do, and they mess around and figure out how to build one. Then you got a TV. So anyway, that's what that's about. So here we need to, of course, if you're thinking about like what about gravity? Gravity is like this is so light that the gravitational force on this is completely negligible compared to this force. So we don't even have to pay attention to that. So if it's going this fast, then what we need to know is how long does it take it to go the 3 centimeters, or 0.03 meters, which is probably the length of the little cathode ray tube here. So how long does it take it to go that far? Well, the velocity this is its horizontal velocity. So this is really kind of like a projectile motion problem. If I want to know the time, I know that, let's see, Vx is equal to delta x over t, so t would be equal to this delta x divided by that. So the delta x divided by 1.2 times 10 to the 7th is not long. That's 2.5 nanoseconds. All right. And so what's going to happen if it's got this acceleration from this? Let's see. So sum of all forces in the y direction is equal to mass of that electron times its acceleration in the y direction. So its acceleration in the y direction is going to be that force divided by that mass. So that's 4.5 times 10 to the negative 16 divided by 9.11 times 10 to the negative 31st. So its acceleration is a whopping 4.9 times 10 to the 14 meters per second squared. And we want to know how much it gets deflected. So that would be its delta y. So its delta y is going to be equal to 1/2 at squared plus vit, but the initial vertical velocity, it comes in horizontally. So just like a projectile motion problem where something is launched horizontally, that's 0. So my delta y, how much it's deflected, is 1/2 times this whopping acceleration, but it does not get to do that acceleration for very long. And let's see how we did. I got kind of a bad feeling about this, I'm not going to lie. 0.9 is 10 to the 14 squared. It's 0.9. Yeah, that's not right. Supposed to get 1.5 millimeters here. What did I do? Did I not convert some units here? That's kilograms. That's newtons. Let's see. What did McGrath do? Acceleration. Did I mess this up? Let's see, the time should be, no, I don't think I messed that up. Well, maybe you can figure out what I did wrong. I know I've done this problem before and got the right answer, so it's probably, you probably know exactly what it is. Don't you? Oh, I know what I did. Yeah, you are probably jumping up and down right now saying, hey, dummy, you just squared the wrong thing. Alright, so that should be easy to fix. let's fix it. So I've got 1/2 times 4.9 times 10 to the 14 times 2.5 times 10 to the negative 9 squared. There we go. So 0.0015 meters, which is 1.5 millimeters. Alrighty, there you go. That was a long one. Hope that was helpful.